Hi guys, today we've got a funky integral. So we're integrating from 1 to n, so 1 to 10, sorry, uh, x times the floor function of x, and all of this applied to the floor function with respect to x. Right, I wouldn't know how to integrate any of this, so what we do is let's sketch and see what happens. So we've got, let's shift that a bit over, and so essentially you've got where we've got the floor function, so it's best just to go up in 1, so we're integrating from 1 to 10. So when we plug in 1, well, we just get 1. So let's put that here. Oops. So let's start with 0 here, then just start at 0 here. So when we're at 1, we have the point 1. And how long does this go on for? Well, as 1 gets larger, so as we go to 1.5, well, we have 1.5 times 1, which again is 1.5, floor that is 1. Then we go up to 1.9, 1.9 times 1 is again 1.9, floor that we just get 1. So from 1 up until 2, we've just got our y value as 1. Now let's go on to when x is 2. So as soon as x is 2, we have 2 times 2, which is 4. So we go up to here. And we'll just go on, if we go to 2.1, 2.2, 2.3, 2.4, we have 2.4 times 2. And if we mod, that's 4.8. Floor that, we still get 4. But actually, let's space this out a little. Let's have 2 there. So we said up to 2.5. Well, let's check. So we have 2.5 times 2, which is 5. So that means we go up 1. And then if we move towards 3 now, so we have 2.9 times 2, which is 5 point, sorry, no, that is 5.8. So we're with 5 from 2.5 up to 3. So we just draw that. Alright, that's fine. Now what happens when we have 3? Well, we have 3 times 3 is 9. So moving a bit up. And at 3, so we just have So with 3 now, well, we need to check between the values of y between 3 and 4. So we can start off 3 times 3 is 9. When our value would change to 10 is when we have x as 3 and 1/3, which is the same as 10 over 3. So we'll go across here a third. And then when we're on to 10, we're outputting 10. And this will happen up until, just right here, that's 10 over 3. So this would happen to 11 over 3. Why is that? Well, if you have 11 over 3 times 3, we have 11. So yeah. So we need to sketch between 10 over 3 and 11 over 3. So when we have 10 over 3 times, well, the floor of that is 3. So we have 10 over 3 times 3, which is 10. So we're going up until here. And then now we're on to 11 over 3 till 4. There we go. We're up to 11 now. Now, of course, we're trying to find the area under this graph. So let's start sketching what we're after. So we're after this area here. This area here. Plus this section here. And then again, we're after all of this area here. And these extra sections. I think it'd be helpful to just box off our sections. So, let's write this in green. So we've got from 1 till 4. We have to deal with these areas. Now I don't think it'd be useful for us to sketch from 1 to 12, as that will be long. So what we would do instead is just evaluate from 1 till 4. Now notice the area of the red bit here between 1 and 2 is just 1 times by 1, so 1 times 1 squared. From 2 to 3 we have 1 times 4, and that's the same as saying 2 squared. From 3 till 4 we have 1 times 9, which is the same as 3 squared. And we can assume that from 4 to 5 we would have had 4 squared, and then so on and so forth. So we've checked the area of our red parts of our graph. Now in the blue. So let's look here. We've got this blue box is a half wide and only 1 and just 1 up. So we've got a half. Now these boxes are each third wide, but one's 1 in height, the other's 2 in height. So we can say 1/3 and 2/3 is just 3 over 3. Now, if we were to sketch between 4 and 5, well, you see how from 2 to 3 we had our box was half, well, 1 divided by 2 times wide. From 3 to 4 our box was 1 over 3 times wide. So we can say that from 4 to 5 our box will be 1 over 4 times wide. And the top bit, right, well, we would imagine there would be boxes like such. So we'll have a box like this, box like this, then a box like this, which would have heights 1, 2 and 3. So that means we've got a height of 6 in total, times by a base of 1/4. So that'll give us 6 over 4. So blue, 6 over 4. Let's start writing out these areas. So if you write our red areas out, we have 1 squared plus 2 squared plus 3 squared up until, well, we're going up until 9, and from 1 to 2 you have 1 squared, 2 to 3, 2 squared, 3 to 4, 3 squared, from 9 to 12, 9 to 10 we'll have 9 squared. Alright, that's fine. Now what about our blue parts? Well, our first one had area 0, because we can just say that was our starting point. Our second had an area half. A third, area 3/3. Our fourth, 6/4. And now, since we've got exact 9 like different, we've got 1 to 2, 2 to 3, 3 to 4, let's say 9 times, we can say that this goes up until over 9. Alright, fine, so we know that the denominator is just n. What about our numerator? So when we had lower bound 1, we had 0, lower bound 2, we had 1, 3, we had 3, 4, we had 6. 1, 3, and 6. Now notice, 1 was formed by using 1 block, 3 was formed by using 3 blocks, and you can sort of see this pattern increasing like steps. So every time we're adding 1 more than we did last time, and we know these to be triangle numbers. Alright, so we would have had 1, 3, 6. Now the rule for triangle numbers follows this: n times n plus 1 over 2. Now let's check. When n is 1, 1 times 2 divided by 2, which is 1. Fine, it doesn't perfectly align because we started at 0/1. That's fine. So we can just say this is 1, and we need to go up until 8, because we have 1 to 9. We need to check our numerators for 8. So 8 times 8 plus 1, so 8 times 7 over 2, so 56 divided by, 8 times 7, 8 times 9, 8 times 9 is 72, divided by 2 is 36. Now we need to evaluate these two areas. So for our red area, well, we've just got the sum of squares, and that formula is as follows: n times n plus 1 times 2n plus 1 over 6, and our n here is 9. So we've got 9 times 10 times 9, 2 times 9 is 18, all over 6. Is that correct? Yep. Right. 1 squared plus 2 squared. Yeah, that's fine. So if we evaluate this, 9 divided by 6 gives us 3/2, which gives us 10 divided by 6. Well, how do we evaluate this? So 6 becomes 2 times 3. 3 cancels with the 9 to give us 3. 3 times 5 times 19. 19 times 15. So we can just do 200 times 15 minus 15, which is 200 times, what am I saying? Let's do this slowly. 5 times 19 is 95. 95 times 3 is 285. That's all our red areas evaluated. Now we've got sort of a more trickier area. So we've got the sequence 0 over 1, 1 over 2, 3 over 3, plus 6 over 4, over 2, 36 over 9. We've got 9 terms in total. Well, we know our first and last term, so we can use this sum formula. So we have n over 2 times a1 plus an. So n in this case is 9. So we've got 9 over 2. Is that right? Yeah, 9 over 2 times 0 plus the last term was 36 over 9. Oh, 36 over 9 we know is just 4. So 9 over 2 times 4 is indeed 18. So now let's sum our two areas. 285 plus 18 equals, quick maths, 303. That is the area of this integral from 1 to 10 without using any integration techniques. That was a fun question. I like how you broke our sketch into squares, perfect squares, and blocks, where the blocks follow the perfect numbers pattern. That was quite nice. Yeah, that was it for today. Hope to see you in the next. Bye.